So previous class we started discussing space vector modulation technique for 3-level inverter. Right. So in case of 3-level inverter, we consider a diode clamped inverter as an example. Right. So we have three different states. We have this positive state, 0 state, and this negative state. And this is the corresponding switching states for S1, S2, S3, and S4. And it is its corresponding.
Sir, screen is not visible, sir.
Now it is visible.
Yes, sir.
Yes, sir.
Right. So previous class we started discussing space vector modulation technique for 3-level inverter, right? So we consider neutral point clamped as an example. So in this NPC we have three different states: positive state, 0 state, and a negative state, right? And these are the corresponding switching status for S1 to S4, and its corresponding terminal voltage or the voltage between this A to this neutral point Z. So we have E, 0, and minus E, three levels. So with this we identified, so there are 27 switching states, right? So there are 27 switching states. So those 27 we have divided into different categories. So 0 states, right, or in other words 0 switching vectors: 0 vector, small vector, medium vector, and large vector. Right. So we already discussed that we have 12 small vectors. We have n-type small vector and p-type small vector, and its magnitude is 1/3 Vd. Similarly, we have this medium vectors. We have 6 medium vectors, and its magnitude is 1/√3 Vd. And we have another 6 large vectors, and its magnitude is 2/3 Vd. We have also 3 zero vectors. So the combined one is total, we have 27 vectors, right? So we also arranged this in space vector diagram. So we have the small vectors here, medium vectors here, and these large vectors here, and these zero vectors are placed at the center of the space vector diagram, right? And this is with their corresponding switch states. So we have these three, right, and we have these two switch states: positive and negative, p-type small vector and n-type small vector. So this is one, this is another one, right? So here the space vector diagram we divided into 6 sectors, starting from sector 1 to sector 6, and each sector again we are divided into 4 regions. In this particular case, if you select one, so one sector 1, sorry, region 1, 2, 3, and 4, right? It's clear. So we also discussed the effect of neutral point voltage on the effect of different vectors, these medium vectors, large vector, and small vectors on neutral point voltage. So how they are actually influencing the neutral point voltage. So that also we discussed in previous class, right? So in this class we will continue the SPM. So before that, right, okay, so let us assume that, right, so let us assume that the reference is false in the sector 1. So before that we need to define the modulation index. Okay, so what is the maximum voltage from this you can get? What is the maximum voltage you can get from this? What is the maximum voltage with this? What is the linear range of this one? So that is this circle, right? You remember when you are discussing the 2-level, so what is the radius of this one? What is the radius of this circle?
Yes,
so that is equal to its magnitude, right? So we already know that its magnitude is 1/√3 or Vd by √3. So that means the maximum voltage we can get is So that is Vd by root 3. So how modulation index is defined? So modulation index usually defined as V reference by V maximum. Okay, V reference by V maximum. So V reference by, so V maximum is, so this Vd by root 3. So that means we have this root 3 V reference by Vd. Okay, so this is the modulation index V reference by V maximum. Right, so up to here the modulation index is 1. Right, so beyond this point, so it will go to over modulation. So beyond this point, it will go to over modulation. So from this point onwards, again it will come to square wave operation. Right, same as what we discussed for 2 level. So here up to, so we get the linear range of modulation index. So from here to here, non-linear range, that means the over modulation. So after that, this point onwards, so it will operate as a square wave. Clear? So that is how we define the modulation index. Some, maybe in some cases we usually in some other way to define is, so this entire thing, right? So starting from here to here, so sometimes so they define as a modulation index. So that modulation index usually capital MA, right? So maybe here, so they define the linear range from here to here onwards. So that is non-linear range. Okay, so just ignore this one. So most of the cases we define, so this one as the modulation index, so that we can easily identify the linear range. So 0 to 1 is the linear range. So beyond 1, so that is non-linear range of the modulation, right? Okay, right. So let us assume that, right? So let us assume that the V reference is false here. V reference is false here. So this is your V reference. Okay, right. So you already have one V reference, just ignore that. So assume that this is V reference. So that means the V reference is in sector 1 and region 1. So your V reference is in sector 1 and region 1. Right. So how this V reference can be written in terms of the 3 vectors. So how we will means how we will define this, means how these V reference composed of different vectors. If you notice that we have this V0 vector is there, so the nearest vector is V1 and V2. Okay, so this is in sector, is in region 1, so that can be, if it is in region 1, so that can be decomposed with V0 vector, V1 vector and V2 vector. Okay, similarly if it is in region 2, right, for example it is in region 2, so which vector we can represent if it is in region 2? So we can represent with V1, V2 and V7. We can represent with V1, V7 and V2. So these are the nearest vectors. So you can also consider this V0, V13 and V14, right? So but these are far away from this actual point, right? So if you consider this one, so in that case the harmonic performance is not good. So just remember that, so we need to consider the nearest space vectors. We need to consider the nearest space vectors. That means V1, V7, V2. So we'll see, so what will happen if we consider, so for region 2, if you consider V13 and this V14, so in that case the harmonic spectrum or the harmonic performance will be degraded. So it will only improve. So when you consider this nearest vectors, that is V1, V7 and V2. Similarly, if you consider the region 3, the nearest vectors are V1, V13 and V7. And it is in case of region 4. So now we can write as V2, V7 and V14. Okay, so these are the nearest vectors in sector 1 for different regions. Okay, so if you notice this region 1, so in this case you have one 0 vector and 2 small vectors. V1, V2 are the small vectors, right? In case of this region 2, so it is V1, V7 and V2, V1, V7 and V2. So in this case, this V7, V2, sorry, this V1, V2 are the small vectors and this V7 is the large vector, right? This V7 is the large vector. So that means, so this one, first one can be represented with one zero vector and two small vectors. So whereas here, so this is represented with two small vectors and one medium vector. And this region 3, so this is V1, V13 and V7. So that means one small vector, one medium vector and one large vector. So here also this V2, so one small vector, one medium vector and one large vector. Okay. So that means what you understand that, so in case of region 1 and 2, you have two small vectors, right? In case of region 1 and 2, you have two small vectors. For region 3 and 4, you have only one small vector. Okay, you have only one small vector. Just remember that. Okay. Right. So let us calculate the switching sequence. So for this, so let us assume that, so that is falls in the sector 1, region 2, right? So sector 1, so region 2. So in this case, the nearest space vectors are this V1, this V7 and V2. So V1, V7 and V2. So as already discussed, we have two small vectors and one medium vector. Okay, right. Similar to the two level, so we assume that its dwell time is Ta and its time is Tb and its time is Tc. Okay, its time is Tc. So we have this relation Ta plus Tb plus Tc equal to Ts, right? So this Ts is the sampling time. So here also this reference vector is varying, right? So here also this reference vector we have sampled here and this time duration is Ts. Okay. So this Ts is obtained from the your sampling period, that is obtained from the sampling frequency. Right. It's clear? So we can write something like this, right? So this V1 and its dwell time Ta plus this V7 and its time Tb and this V2 and its time Tc. So this is equal to this V reference, right? So this V reference into its time Ts. So you have this one equation. So this is another equation. So you know the value of V1, right? So what is the value of V1? So this V1 is, what is its magnitude? 1 by 3, right? So its magnitude is 1 by 3. What is its magnitude? 1 by 3 e to the power of, so its magnitude is 1 by 3 Vd into e to the power of J0, right? Similarly, this V7 is 1 by 3 Vd into e to the power of J pi by 6, right? Similarly, this V2 is not 1 by 3, it's 1 by root 3, and this is 1 by 3 Vd into e to the power of J pi by 3. Okay, so all these values are to you, right? This V1, V7 and V2 are known to you, right? So you need to substitute in this equation. So along these equations, you need to solve for Ta, Tb and Tc. You need to solve it for Ta, Tb and Tc. Right. So once you solve this one, right? So once you solve this one, so you'll get the values for Ta, Tb and Tc in this format. You need to separate the real and imaginary terms. You need to separate the real and imaginary terms for the V reference. So you will get, so these values for Ta, Tb and Tc, and this is for the different regions. You have region 1, 2, 3 and 4. So this example is for sector 1. Okay, in sector 1, so this region 1 is for V1, V0, V2. Similarly, the region 2 is V1, V7, V2. So region 3 is V1, V7 V13. We have for region 4 is V14, V7, and V2. So these are the timings, right? So these are the timings for the, means these are the dwell times for to obtain a V reference vector in sector 1 for the different regions. Okay, clear? So once you obtain these timings for this TA, TB, and TC, so what is the next step is? What is the next step? We need to provide the design sequence, right? We need to provide the design sequence, right? So we need to provide the design sequence. So here also we will have some rules. We will formulate some rules for this this design. So what are those rules are? So we have formulated some rules. So what are the rules are? The transition from one switching state to the next switching state involve only two switches, right? So one switching is being turned off and the other switch is being turned on, right? So that is same as two level. So one, it is changing from one switching state to other switching state, right? So in this interval, this is one, right? So we are divided into simple switching state, right? So when it is changing from this switching state to this switching state, or one TS to other TS, so it involves only, right? It involves only one switching state to be changed, right? And the transition from V reference moving from one sector to other sector, right? So when it is moving from one sector to other sector or one region to other region, so it requires only minimum number of switchings. It requires no or minimum number of switchings. So that is common. So whatever we studied for two level, so here also, so that is common. So extra thing is, right, so the effect of switching state on the neutral point voltage, so we need to minimize, right? So we need to minimize the effect of neutral point voltage. We need to minimize the effect of neutral point voltage. Okay, so we have formulated three constraints. So first one is transition from one switching state to the next switching state. So that involves only two switches. So that means two switches in the same inverter leg. So one switching being turned off and the other switch is being turned on, right? So that is one thing. And transition from V reference, when it is moving from one sector to other sector, or when it is changing from one region to other region, it involves no switching or minimum switchings. And the third one, so this is extra, right? So this is the effect of switching state on the neutral point voltage. It should be, means this must be minimized, right? So we need to select, we already discussed that this large vectors, right, and zero vectors will not influence the neutral point voltage, right? So medium vectors will influence the neutral point voltage, right? But whether they are increasing or decreasing, so that is undefined, right? But these small vectors will influence the neutral point voltage, right? So that depends on the current direction. If the one p-type vector is increasing the neutral point voltage, so that n-type vector will decrease the neutral point voltage. Okay, if p-type vector is increasing the neutral point voltage, the n-type vector decreasing the neutral point voltage. So how we are formulated that in one, right, in one period of time, if you use the p-type vector, right, and some other period of time if you use the n-type small vector, so in that case the neutral point can be minimized, right? So that is what here. Okay, so this is the switching sequence for the sector 1 in region 4. So this is corresponding to sector 1 and region 4. Okay, so this is sector 1 and region 4. So that means this is composed of this V2, V7 and V14. Okay, it is composed of V2, V7 and V14, right? So that means in this case this V2 is the small vector, so this V7 is the medium vector and V14 is the large vector, right? So this V2, we have two options, P type and N type, so that is PP0 and 00N. So let's see so how this switching is designed. right? So this is n type. So what they did is, right, so p type, so this 12 times is, it is a 7 segment switching sequence, 7 segment switching sequence. So that means the TA is divided into 2 parts usually, right? And this TC is also, TB is divided into 2 parts, but this TC is divided into 3 parts, right? This TC is divided into 2 parts. So we can change this one, right? So let us assume that this TC is there, right? Okay. So in this TC, so again this is divided into 2 parts. So that is TC by 2, the 3 parts, TC by 4 and TC by 4, right? So first it will start like this. Okay, in the first TS period, so we'll start with this 00N. Okay, so we'll start with this 00N here. So that means in this V2 vector, we used the N type, small vector here. So next one is 00N, right? So therefore, if you want to have only one transition, so we can choose this V7, so that this is P0N. So that means we need to change only this 0 to P here. And next we choose this V14. So again, there is a change in this middle one. Okay. And after here, so this is PP0 we selected. So here we selected N type, but here you selected P type. So here we selected N type, but we selected P type here. Again this V14, so this is PPN, so only change here, and this is V7, and here also, so only change in the middle one, and it is ends with 00, and again this is N type. Clear? Right? So we are carefully used these small vectors. So we are carefully used these small vectors, right? So here it's off of this means off of the period we have N type vector, and remaining of you have this P type vector. So here instead of this PP0, you can also choose this N type vector. That if you choose this 00N, so what could be the resultant? What could be the resultant if you choose 00N here? What will happen?
In next stage, there will be two switching operators.
There is two transitions, right? This is PPP, right? And now it is changed to 00, right? So that means two legs are affected. So that is one point. And moreover, for example, if you use N type, the neutral point voltage is increasing here, right? So here this neutral point is increasing. So here also it is increasing, and here also it is increasing. Okay, so that means there will be chance that that neutral point will be increased. If we use P type, so if in this case if it is increasing here, so in this case it is decreasing, and here it is here it is increasing again, right? So that means the balance can be achieved. So we can achieve some balance, right? So this is one example of switching sequence. We have N type, we have several types. So this is usually followed. So this is 7-segment switching sequence. Right. So switching sequence is divided into 2 parts. This is TA by 2. Again, this is TA by 2, TB by 2, TB by 2. So the TC, the small vector, is divided into 3 parts. You have TC by 2 here, and this is TC by 4, and this is TC by 4. Okay. So this is one of the method normally they use, right? So this is one of the method out of so many methods. Okay. So if you notice that this is starting from 00N, and whereas it is ended at 00N. Clear? Right? So in this case, right, so this is for sector 1 and region 4. Sector 1 and region 4. So that means you have one small vector, one medium vector, and one large vector. Right. So this small vector, right? So this is a small vector, right? So this is medium vector, and this is large vector. The small vector we divided into 3 parts: TC by 4, TC by 2, and TC by 4. But this medium vector we divided into 2 parts, and this large vector we divided into 2 parts. Okay, in small vector, half of the period we operate p type, and another half we operate n type. Okay, this is fine. So what about, right? So what about if we have, if it is in region 2, so what we have to do? If it is in region 2, what we have to do? Or if it is in region 1, what we have to do in this case? For example, if it is in region 2, so this can be decomposed with, or this one with V1, one small vector. So this is another small vector, and this is one medium vector, right? If it is in region 2, so here has two small vectors and one medium vector. Or if it is in, this is for region 2. If it is in region 1, so in that case also we have two small vectors and one zero vectors. Okay, so under this particular cases, right? So how to implement that 7-segment switching sequence? How to implement the 7-segment switching sequence? Right? So again, this small vector, there are two small vectors, or this medium vector will divide into two parts, right? So these two small vectors are there, right? So one we need to divide into three parts, and the other one we need to divide it into two parts. One small vector we need to divide into three parts, and the other one we need to divide into two parts, so that we have these 7 segments, right? The question is, so which one we need to divide into three parts? Or in other words, so which one we will implement the positive and negative type small vectors? Okay. So if you notice that, right, so for example, this is the V reference. This entire thing is 60 degrees, right? So we can divide it into 30 degrees and 30 degrees. For example, it is somewhere around 15 degrees. Okay, if it is in 15 degrees, right? So which vector will influence more? Which vector will influence more? In other words, in this TA, TB, and TC, so which value will be more? Or this TA value will be more, or TC value will be more?
Yes, sir.
Yeah.
Here, right? So that means it's predominantly this reference vector is depends on this V1. Similarly, when it is from 30 to 60 degrees, so in that case, it is predominantly, so depends on this V2, right? So that means in this case, this TA is greater than this TC. So whereas here, this TC is greater than TA. Okay, if it is for this is for 0 to 30 degrees, and this is for 30 to 60 degrees. Okay, for exactly 30 degrees, the TA and TC values, so both are same, right? Okay, so now what we have to do is, if it is in region 2, so again we will divide it into two parts, right? So this region 2 we divide it into two parts. Say it may be 2A, 2B region. Okay, so for example, it is in 2A region, that is for first 30 degrees, and this is for 30 to 60 degrees, right? So this is 2A region, and this is 2B region. For example, it is in 2A region. This is V1 is having stronger influence, right? So that means the TA is more, right? So this TA is more. So in this case, what we have to do is, so this TA we divide it into three parts, and this TB we divide it into two parts, and TC we divide it into two parts. So in this TA, again, right, half of the period we will implement the N type, and remaining half we will implement P type. Okay, it's clear. So this is the particular case where we have two small vectors, right? So in which small vector, whether you actually implement this P type and N type, right? So that depends on, so which is having the stronger influence, which small vector is having the stronger influence. So that will decide, that vector is divided in this, that vector we need to implement P type and N type, so that we can reduce the neutral point voltage to some extent, right? Clear? The same thing for this one, this region 1 also. Again, you have this 1A and 1B. Clear? It's clear? This is clear?
Yes, sir.
Okay.
Yes, sir.
So let us see some one of the example switching sequence.
Sir, screen is frozen.
Mhm.
Sir,
Yes, screen is frozen.
Yes, sir.
Now it is shown.
No, sir.
Now it is visible.
Yes, sir.
Now it is visible. So this is what we discussed, right? So we divided this one region 1 and region 2 into two parts. So this is 1A, right? And this is 1B, and this is 2A, and this is 2B, right? In case of 1A and 2A, so this V1 is having the stronger influence. In case of 1B and 2B, we have this V2 having the stronger influence, right? So this is the sequence, right? So this is sequence for the sector 1 in different regions. Again, this region, what we discussed, this 1A, 1B. So this is for first 30 degrees, and this is for the next 30 degrees. This is 2A, 2B, this is 3 and 4, right? So in case if you have selected 1A, right? So if you selected 1A, so if you selected, if it is in 1A, right? So that means this V1, its corresponding time is TA, right? That means the V1 we need to implement, so both P type and N type in 1A. If it is 1B, so we need to implement V2P and V2N here. Okay, so here V1P and V1N here. So in 1A, we need to implement V1P and V1N. In region 2, so we need to implement V2P and V2N. The same thing, so what it describes, there are 7 segments, right? This is first 2, 3, 4, 5 up to 7. So this is V1, this is V1, right? And this is another V1. In between this V1, P here. Clear? Okay, right? So B2 is also small vector, right? So this V2 is also small vector, but we are not implementing any. In case we are implementing only this negative, right? So only N type we are implementing. So why N type we are implementing? If you use P type, so in that case the switching losses will be increased, right? So here also we used N type. So because the state is 0, 0, 0, right? If you use P type, right? If you use P type, that is P 0, 0. So in that case the switching losses will be increased for the subsequent segments. So therefore we implement only N type for the V2 vector. For the V1 vector, we implement both P type and N type. For the same thing, if it is in 1B, right? If it is in 1B, so this V2, right? We have implemented V2N here, V2P here, and this is V2N. Okay, so here this V1 is divided into P type and N type. So this V2 now it is divided into P type and type. Similarly here, this is for 2A. So again, this V1 is divided, and here this V2 is divided into P type and N type. Here, so only one small vector is there. So in this case, only V1 is implemented. V1 is divided into two parts, and here this V2 is divided into two parts. It's clear? It's clear. So this is how the switching sequence is generated. So this is how the switching sequence is generated. So with reducing the neutral point voltage. Okay. So however, so with the space vector modulation technique, we cannot completely balance these two capacitor voltages or these two DC sources, right? There are methods are there to balance these DC sources, so that we will discuss in the later classes. right? Okay. So with SVM, we can reduce the neutral point, or we can slightly balance these two DC sources. So upper capacitor voltage and the bottom capacitor voltage. So with using these different p-type and n-type space vectors, but you cannot completely balance those, because if it is in one segment, for example, if it is in 1A, right? If it is in 1A or 1B, right? If it is in 1A, 1B, or if it is in region 1 and 2, so in that case, so here it is continuously increasing, right? So in this case, it is continuously increasing. So here also it is continuously increasing or decreasing. So there is no control here, right? Where you are provided the control for the V1 vector, but you are not provided the control for this V2 vector. So therefore, it may cause the capacitor voltage, it may cause some unbalance in the capacitor voltage. But whereas in for 3 and region, if it is in region 3 and 4, okay, if it is in region 3 and 4, so in that case we can operate with or we can reduce this neutral point voltage, means we can reduce the unbalance among these two capacitor voltages, right? Clear? So usually, for example, if the modulation index is very small, right? If it is always operating like this, so in this case, this problem especially visible, this capacitor voltage problem especially visible. For example, this is the V reference. For example, this is V reference. Okay, this is V reference. So what will happen? So it will always with V1, V2, V3, V4, and V5, right? So in that case, it will never go for this medium or this large vectors. So that means always we have two small vectors. So therefore, under low modulation index, this capacitor voltage problem can be so visible. Means it will be more visible. But, it can be more right. So in this case, you can only implement this V1, V2, V3, V4, V5, right? So that means we need to divide this 1A, 1B, 2A, 2B, 3A, 3B, something like that. We need to divide each sector, right? So in this case, the neutral point voltage will be, or this deviation will be very high, right? So that in case of low modulation index, this problem can be seen. If it is beyond this point, for example, this is point, right? So in that case, in some cases only, when it is in this region, when it is in this, especially in this region 2 only, this can be noticed, right? This unbalance can be noticed. It's clear. Right. So this is the same example for sector 2. So again, the sector 2 is divided into 1A, 1B, 2A, 2B, 3 and 4. Right. So if you notice that when it is moving from sector 1 to sector 2, right? So sector 1, this is the ending point for the sector. For example, it is 1A, right? So this is the ending point for the sector 1, right? So this ends with 0 and n. So it ends with 0 and n. This is sector 1 when it is moving from one sector to other sector. That means after first 60 degrees. So this is 60 degrees, it is ended here. So that is 0 and n. Right. So whereas it is started from 0 and n. Okay. It is started from 0 and n. So that means you have one extra switching, right? So normally when it is moving from one sector to other sector, it is expected that so there will be no extra switching. So here is a 0 and n, right? But it is starting from 0 and n. This is 0 0 n. This is 0 0 n. 0 0 n, right? So that means this phase is affected. That means the B phase is affected. So that means it is some extra switching is there. So here also it is starting. It is ended at 0 0 n, but it is started at n0 n. So there is where extra switching. But in case of 3, right? In case of region 3, So here also in case of region 3, it is ended at 0 and n, right? But it started at 0, 0, n. So here also it is 0, 0, n. So there's some extra switching is happening. So when it is changing from one sector to other sector. So usually this extra switching will not be occurred in case of 2 level. So but in case of the 3 level, so this extra switch is there. And when it is changing from 1A to 1B, okay, so when it is changing from 1A to 1B, so obviously this change, it will change from 1A to 1B, right? If this is the reference vector, so this vector will move like this, right? So when it is changing from 1A to 1B, let us see what will happen. So this is 1A, so 1A is ended here, right? So 0 and n, okay, so that means this 1B started like this, right? So this is 0, 0, n. So that means again you have one extra switching. So that means when it is changing from one region to other region, so you have extra switching. When it is changing from when it's changing from one sector to other sector, you have another extra switching is there, right? Clear? So this is the points. So where you have this extra switchings, right? So this is the point where you have this dots, right? So this dot is extra switching, right? When it is changing from 2A to 2B, you have extra switching. So here also you have extra switching when it's changing from 2A to 2B. So here also you have extra switchings. So these are the extra switchings. Okay. Similarly, when it is changing from 1A to 1B, 1B, so here also you have one extra switchings. Clear? It's clear?
Yes, sir. Yes.
Right. Okay. So these are the outputs, right? So this is the output voltage. You can see this is the uh, I think this is the neutral point. This is pole voltage or the voltage between the A phase and this neutral point VAZ, and this is the line voltage. Line voltage is changing from 2E to minus 2E. You can see it's harmonic spectrum here. Okay, so this is for A to Z, and this is for phase voltage. You can see some small some small value, some small even order harmonics present here. Okay, so again this even order harmonics, we can eliminate these even order harmonics like what we followed, right? Okay, if you use n-type and p-type switching sequence, right? If you use n-type and p-type switching sequence, that is type A sequence and type B sequence, so that's what we followed, right? In case of two level, we followed this, right? Type A switching sequence and type B switching sequence to eliminate these even order harmonics, right? Similarly, it is divided into three parts. So in case of this type A switching sequence, that is for the first 0 to 30 degrees. So we follow this n and 0. Start from n. This is n00. 0. Started from n00 here. Started at n0, and again it is ended at n0. So this n-type sequence, right? It start with n-type small vector. So that is vn0 here. The same thing. Right. So when it is for 30 to 60 degrees, right? So this is 00 here. Sorry, 0 pp here, and it is ended at 0 pp. So if you notice that when it is changing from type A switching sequence to type C switching sequence, it's n00, right? To change it from n00, right? And again it started at 0 pp. Okay, so this is started at 0 pp. So there are two types of switching sequence that what we discussed. It's an n-type switching sequence and p-type switching sequence. This is same as this is for first 30 degrees. For the first 30 degrees, so we follow this type B switching sequence. For the next 30 degrees, we follow this type A switching sequence. Clear? So when we are going from this type A switching sequence to type B switching sequence, so obviously, so there are some extra switchings. So we'll occur. अभी मैं क्लास में हूँ, बाद में कॉल करता हूँ, ठीक है? I'm audible?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So we need to
Sir,
use this different switching.
Sir, I
Yes.
have a doubt. Sir, actually, in this, when we are changing from sector to sector or region to region, extra switching is taking place inside in this.
Yeah, yeah.
Because of that extra switching, even harmonic should not be there inside. But again, we are doing extra switching to reduce that.
See, this extra switching is actually not there in this 3 and 4, right? Normally, this one is not implemented, right? So this is different and that is different. Okay. So even though this 1A, 1B, we are use it to eliminate the, or we need to reduce this neutral point voltage, right? Okay. With this, you cannot eliminate the even order harmonics. So with this switching sequence, you cannot eliminate the even order harmonics. So that can be normally eliminated. So when you follow this type A and type B switching sequence. Okay. So in this, it is so this is what one of the example, right? It started. This is type A. It is a type A switching sequence, and this is type B switching sequence. So with this one, so we can eliminate the even order harmonics. Okay. So we need to combine both. Okay. We need to combine both.
Sir, is there any disadvantage of having extra switchings in this diode plan? Having
If there is some extra switching, some losses will increase, right? If you have extra switches, so obviously the losses increases. So for example, if you have extra switching here, right? So that means we are, instead of changing one phase, we are changing two phases. That some extra switches are there. Okay.
Okay, sir.
So that means how many, for example, in one cycle, how many extra switches are there? 1, 2, 3, 4, 5, 6 extra switching is there, right? In one, every cycle, every carrier cycle, one extra switching is there. In every fundamental, you have 6 extra switchings are there. See, what will happen is there, right? See, this whatever the amount of that loss with this extra switching is very small only. Okay, but a lot of research are continuously changing, right? For example, if somebody has got, it means it is continuously exploring, right? For example, in an overall, for example, 10 kilowatt is the overall loss, okay, for certain inverter. So they're trying, in one step, they're trying to increase or decrease to 10 kilowatt, 7 kilowatt. Okay, they're continuously exploring that, so that whatever this amount of that extra switching, right? So this may not be a very big, right? But from the research research point of view, so that this loss is significant. Okay. They're always trying to reduce the loss, right? So that, so they have special mention on this. Okay. So with this extra switching loss, there won't be much reduce in the energy efficiency. Okay. But the thing is that with this extra switching, so we can balance these capacitor voltages or this DC source voltages.
So we go for this extra switching only when modulation index is low, or we can use it for a higher modulation index also.
This extra switching, if it is modulation index, this is for low modulation index case, right? So this one is the low modulation
sir.
index case, right? In this case also we have this extra switching. Okay. In this case, see this extra, for example, see this is how the normally, if you have a rigid DC sources are there, that means you know that the DC sources are constant. Okay. So in that case, all these things, whatever this 1A, 1B, that is not required. Okay. Because they are rigid sources, right? If you are used a batteries here, for example, in this for the source, so they are rigid, right? So that means this battery is usually 300 volts. This is charged some external converter is there that is charged to 300. This is also charged to 300. This voltage is fixed, right? So in that case, you no need to go for this P type or N type. Okay. So this P type, N type, small vectors, all these are only required. So when you have capacitors, okay, so when you have capacitors, so then only this one will come. If you have a DC or it is a motor drive application, so in that case we have these voltages are usually fixed, right? So this is supplied from a front end converter, that is 12 pulse converter. So these voltages are fixed. In that case you cannot change the neutral point voltage with the current that flow. So that means this extra switching or this whatever this you don't need to divide this 1A, 1B, 1, 3, that directly you can implement that 7 segment. Okay. So this whatever this P type N type, so that is only required. So when you have that is not required when you have fixed sources, right?
So which
So
one is
usually
better,
this
sir, to use?
yes,
Using switch fixed sources, is it better to use, or having capacitor voltages?
that all depends on the application, right? So if it is a motor drive, so that means continuously you need to feed it, right? Continuously you need to supply power, right? So in that case you need to use a active front end, right? So this is what we discussed, I think. Yes, this one. So this is 3 level, right? This is 3 level. Okay. So but the thing is that, right? So but the thing is that, so this is fed from a AC source, right? So this is fed from a DC source. This is because the application is a motor drive. So continuously this AC is converted to DC here, and this is converted back to AC. So that means this is DC link, right? Okay. Usually this point connection is usually there. Okay. So that means this voltage you can't change, right? This voltage depends on here, and this voltage is depends on here, right? So usually these are rigid. Okay. So usually these DC sources are rigid. So this diode bridge rectifier is charging this capacitor, and this diode bridge rectifier is charging this capacitor. So that means these voltages are rigid. Okay. So in that case, you no need to go for this P type or N type. Okay. For example, if this is not there, this front end is not there, and this application something different, maybe it is a PV application or some grid connected application or something STATCOM application, right? So in that case, we have these two are capacitors, right? So in that case, so there is no auxiliary supply to this capacitor. We need to balance this capacitor. That means the capacitor voltage may be changes depending on the current flow in those. In that case, we need to go for these balance circuits. Okay.
Okay.
That we discussed in the first class, I remember. we discussed one application, right? I think this one. Yeah. So this is active power filter application, right? So this is active power filter application. Right. So this one actually, this is active power filter. Okay. So this one actually it will not draw any power. Okay. So it will not draw any power. So just it will draw the power that's sufficient to balance or that are sufficient to maintain the capacitor at some fixed voltages. Okay. There is no usual. Ideally, there is no real power flow. Okay. That means there is no real power flow from here to here. Only reactive power flow. But whereas the real power flow from this is source and this is load. Okay. Real power actually flow here. Okay, so reactive power, whatever that reactive power that is circulated between these two, so that load and this converter. From the source point of view, the reactive power is 0. So that means that from source point of view, it is not drawing any real power. Okay, so in that case, we need to balance these two capacitors. Okay, so then only so this capacitor balance problem can occur. Clear?
Yes, sir.
Okay, you have any doubts on this? You have any doubts on this? Okay, I will stop here if you have no doubts.